Hello everybody, welcome back to another video. Today we're going to be looking at the grade 12 May-June question paper 2. This is for the year 2024. Alright, we are continuing with cyclic geometry on question 10. Okay, the statement of the question reads as follows. In the diagram, COD is the diameter of the circle with center O. EA is a tangent to the circle at F, right? Here's the diagram. They are saying there is COD, which is the diameter with center O. And we can clearly see that this line starts from the circumference to the circumference and passes through the center O, and that is a diameter. We're also told that EA is a tangent to the circle at point F. EA is this line. It is external to the circle and only touches the circle once at this point F here. Right. Now diameter COD produced intersects the tangent to the circle at point E. Alright, so COD is now extended to DE and then it intersects the tangent at the point E. Alright, so CF intersects OB intersects the tangent to the circle at point A. So we have OB also intersects the tangent EA at the point A. Alright. We also have the line CF, which intersects OB at point T. CF intersects OB at the point T. Alright. There is CB, BD, OF, and FD, which are chords drawn in this diagram. All right. The first question is asking us to prove with the reasons that TODF is a cyclic quadrilateral. All right. Where is TODF? TODF is a cyclic quadrilateral. All right. That's the first question. Question 10.1. Prove that TODF is a cyclic quad. This is the question. Right. Now, let's first observe where is TODF. TODF. All right. We can definitely see that there is no circle there. So we need to prove that indeed we can draw a circle. So we can draw a circle at which all those points that are mentioned there are going to touch the circumference of the circle. So if we can draw a circle like this. Right. It is not there. You're supposed to imagine that it is there. And for you to prove that something is a cyclic quad, we need to first make sure that those points that they are mentioning, so that's point T, O, D, F, they touch the circumference of that cyclic quad. Okay, now how do we go about proving something is a cyclic quad? Okay, so for cyclic quad, we know that the opposite angles of a cyclic quad are supplementary. Right. We also know that the exterior angle of a cyclic quad must be equal to the interior opposite angle of that cyclic quad. So if we look at this cyclic quad that we're meant to prove, if indeed TODF is a cyclic quad, the angle, this angle here, plus this angle here, is supposed to give you 180 degrees, all right? Same as T3 and angle D1 and D2. They're supposed to add up to 180 degrees. Another way, we can go for the exterior angle, let's say T4 should be equal to the opposite interior angle. You can go this way. O1 should be equal to F2 plus F3. All right. Another way to prove a cyclic quad is through the angles subtended by the same chord theorem, but we're not going to go for that because we can clearly see that we don't have such a shape in here. All right. So let's look. We can go for opposite angles are supplementary. All right, 1. Or exterior angle is equal to opposite interior angle. Interior angle. Okay. Now what we have in this diagram, we have the angle O1. It is given that it is 90 degrees. Okay. If we were to go for opposite angles as supplementary, we don't yet have T3. We don't yet have angle O3 and O2, F2 and F3, and D1 and 2. So we need to solve that so that we can prove that if you add these two, they can give you the 90 degrees. All right. Another way is the exterior angle. We already have an exterior angle to this cyclic quad. There is an exterior angle. If you look at this line, this angle here is exterior to that cyclic quad. That angle is supposed to equal to the opposite interior angle of the cyclic quad. And which one is it? Okay, let's look at the interior, the opposite interior angle. This is the opposite interior angle of that cyclic quad. All right. Do we have that angle? No, we don't, but can we find that angle or can we calculate that angle? Where is that angle? That angle is at the circumference. Here's the angle. It's at the circumference. All right. And it's within the triangle CDF. So if we look here, in triangle CDF, we have an angle there. We have angle F2 plus F3, or you can call it as angle CFD. All right. That angle there is subtended by a diameter. You see the diameter? COD. It is enclosed by COD. Okay, let's try to draw that. That angle looks like this. Right. This is a diameter. And we know that angles subtended by a diameter, those angles should equal to 90 degrees. Or another way you can say, an angle at the center here, which is 180 degrees, is twice the angle at the circumference, which you can see, this is the angle at the circumference. So we already have the value of CFD. So CFD is equal to 90 degrees. What is the reason? Angle in a semicircle. Right. Or angle at center is twice the angle at the circumference. Okay. So if we have CFD, but we also know that O1 is equal to 90 degrees. We can therefore say that indeed TODF is a cyclic quad. And why? Because of the exterior angle, which is the second way of proving that question. All right. So we can say therefore TODF is indeed a cyclic quad. What is the reason? Exterior angle, the method that we used, is equal to opposite interior angle of that cyclic quad. That is the first question. Now we can move to the second question, which is 10.2. All right, 10.2 is asking us to prove that the angle D3 is equal to the angle T1. Angle D3 is equal to the angle T1. Okay. Angle D3, okay, 10.2, prove that D3 is equal to T1. Where is D3 and where is T1? Okay. We see T1 is at this point. And D3 is this one here. All right. We have just proven that TODF is a cyclic quad. And if TODF is a cyclic quad, it means that the angle D3 is exterior to that cyclic quad. All right. If you look at the cyclic quad, you see that line there, line OE, we have an angle there, D3, which is exterior to the cyclic quad. Okay, what is special about D1? Okay, so D1 exists in this form here. So if you see angle CF and OD, they have a vertex, or they all intersect at the point T. So if you can draw that and say, we have something like this, where T1 is here, this is C, TF and we have OA. This is T1 and there's also T3. What do we know about the opposite angle in a vertex or like in a crossover like this? So these opposite angles are supposed to be equal. But the best way to have a look at this thing is that if we have angle 4 here and angle 2 here, we know that T1, this is a straight line OA, T1 plus T4 should be equal to 180 degrees because those are angles in a straight line. But you also know that there is a straight line there, CF, and we can say T3 plus T4 is equal to 180 degrees. And because of this, you can definitely tell that T1 will be the same. All right, so T1 is equal to T3. These are opposite angles in a vertex or in an intersection like this. All right, so that's the fastest way to prove it. So we already have a knowledge about T1, that T1 is indeed equal to this angle here, T3. But what else is that angle equal to? This is an opposite, this is an interior angle of a cyclic quad. That interior angle of a cyclic quad needs to correspond to an exterior angle of that cyclic quad, or it should be supplementary to the opposite interior angle of that cyclic quad. But if you look here, we don't yet have this angle, and we're asked to prove that this one is indeed equal to this one. All right. So if T1 is equal to angle T3, opposite angles in a vertex, but we also know that D3 is exterior to that cyclic quad, and an exterior angle to a cyclic quad needs to be equal to the opposite interior angle of that cyclic quad. Then we can say D3 is also equal to angle T3, and the reason is that there's an exterior angle. So yes, exterior angle of a cyclic quad is equal to opposite interior angle. All right. If that is the case, therefore we can conclude that D3 is indeed equal to the angle T1. All right. So we have proven that D3 is indeed equal to the angle T1. All right. Okay. So we have proven that angle D3 is equal to T1. We are now asked to prove that the triangle TFO is similar to triangle DFE. All right. Let's go for that question. Is TFO. All right. So 10.3. We're asked to prove triangle TFO is similar to triangle DFE. Okay. To prove similar triangles, we can go for the sides that are proportional. Sides must be proportional. Or all the angles correspond. So we have angles that are in triangle TFO that are also in triangle DFE. So we can go for all angles. All right, for now, let's stick to these first two, and let's see if we can go about proving this question, maybe using one of these two. All right. So to prove that sides are proportional, you need to know what you're doing in terms of, you need to know the values of those sides. So if you look at DFE and TFO, firstly, DF and FE are exterior to that circle, and TF and TO, unlike OF, but TF and are just random sides, and we're not given the units of those sides. So going for proportionality is going to be a long route. Maybe you might be successful, but I don't like long routes. Okay, so let's think of angles. We have been playing with angles from the first question and the second question. Let's see if we can use those angles we got from those questions to prove that indeed we have common angles throughout those triangles. All right. Okay, but remember, on question 2, we're already asked to prove that D3 is equal to T3. and understand that T3 is an angle that is in TFO. And then D3 is in DF3. So we already know that we have the first angle here, angle number A. All right, that is given. We are proving it on the previous question. All right. So we now need to prove that one of these triangles here, let's say O2 or F2 is equal to the other angles that are in DF3. Okay. How do you go about proving that? We can go for angle E. How would we try and prove angle E is one of these angles here? Is there any special thing about that angle E? One can say angle E is exterior to the circle. So we can maybe go for that theorem that says where we're joining two tangents, those tangents or the length of those lines are supposed to be the same, but we don't have two tangents here. We have tangent EA, we don't have another one here. All right. Do we have maybe another way we can go about that angle? We can look for it and probably find it, but let's look at what is special about the angle FO. Okay, where is FO situated? Angle FO is situated between a tangent EA and a chord DF. Does that ring a bell? Tangent and a chord. Okay, so a tangent and a chord relates us to that theorem. The angle between a tangent and the chord should be equal to the interior angle that is subtended by that very same chord, or the opposite interior angle subtended by that very same chord, or the angle in the other segment. Okay, so we can say F4 is equal to C2, but that tells us nothing about this triangle TFO, right? But we know something special about FO. Okay, maybe let's go back to this triangle here, TFO. In TFO, we have angle F2. Okay, angle F2 is between the chord CF and OF. CF and OF. But what is special about these two chords here, or this chord and this line? This is just a mere chord, but OF is the radius. Okay? Understand that the radius at this point is the same as this radius here and the same as the radius there. Radius will always be the same because it starts from the center to the circumference, which can tell us that OC is equal to OF because those are radiuses. And what does that tell us about this whole triangle here? So let's start from fresh. So OF is equal to OC, which is just radi. So these are radius, okay? But that subsequently makes this whole triangle here CFO, triangle CFO. Therefore, triangle CFO is an isosceles triangle. Why? Because those two lines are the same, okay? But we're just talking now that F4 should be equal to C2 because that's a tan chord theorem. But we also know that if this is an isosceles triangle, it means the base angles of the isosceles triangles are the same. Okay, let's follow that trail there. So we have, let's start. C2 is equal to angle F2. These are base angles of an isosceles triangle. All right, but we've just mentioned that F4 is equal to the angle C2. Why? This is a tan. What tangent are we referring to? Tangent EA. Tan chord. What chord are we referring to? Chord DF. All right. Tan chord theorem. Okay. So if C2 is equal to F2 and F4 is still equal to C2, then indeed we can say F4 and F2, those are the same. All right. So therefore, F4 is equal to F2. Now, mind you, we already have proved that D3 is equal to T3. We have two angles now that are common. And as we all know that the angles in a triangle should all add up to 180 degrees. So if this angle is the same as this one, and this angle here, this angle we said is the same as T3. Yes. Then indeed, this one should be equal to this angle here. Why? Because if we say T3 plus F2 plus O2, this should equal to 180. And then we say F4 plus D3 plus E, they should be equal to 180, but these are already common on that side. All right. So therefore, we can say angle E is equal to angle O2. These angles in a triangle should equal to 180 degrees. Then we have proven that indeed, with these two options where they're going for all angles are equal, we can say that those two triangles are definitely similar. Therefore, triangle TFO is similar to DFE. What method did we use? We used all angles. So angle, angle, angle. All right. So those are similar triangles. We can move on to the next question. Question 10.4. All right. Question 10.4 is asking us, or is telling us that if B2, the angle B2 is equal to the angle E, prove that the line DB is parallel to the line EA. Okay. Prove that line DB is parallel to line EA. We're meant to prove that, okay? Well, given that B2 is equal to E. To prove parallel lines, we have, I can say, three options. There's probably many more out there. We can either prove that there's alternate angles. There's angles that form a Z, so this angle here is the same as that one. Or we can go for corresponding angles. That is, I call it the F. ZF and then the U. So these angles here should sum up or are supplemental. So those are basic ways that we know from probably grade 9, grade 10, that we can prove that indeed these lines here are parallel. All right. If we go to that shape, I can already tell that there is a Z there. There is a Z. If you look at this Z here, but will that help me? This Z has F4 and has D2, but this has nothing to do with the information that we're given before. We're given that B2 is equal to angle E, all right? Maybe we can say, okay, this angle here is equal to this one, but we need to prove that. We need to find that angle. And looking at where that angle is situated is going to be a mission. Let's try to look for F. F, we see F here. There is F. We see F here. We also see F here. Sorry. Also see F there. Okay. So we can either prove that B2 is equal to A, but we're mostly interested on E here. We should focus on the angles that are going to align with E or B2. So A, having information about A, really doesn't help us a lot at the moment. Okay? Can we go for this side, which has E? Angle E should be equal to D1. That is the corresponding angles. But we don't have D1. We haven't proved that D1 indeed is equal to E. But that at least aligns us to finding or to linking E to B2. Okay? But we need to find the relationship between D1 and B2. That is the cause, or that is the approach that we can go for. Or we can go for the last one, which is co-interior angles. So these angles here should be supplemental. We don't have D3 or D2. We, as you saw from before, that we ran away from finding D2. All right. Let's try to focus on the F that we see here between D1 and E. Okay. Now, what we know about D1? Where is D1 situated? D1 is in a triangle CDB. Okay. And is also in a triangle ODB. Okay. I can already tell that in this triangle here, we have one long side, which is called a diameter, COD. But diameter, having one side that is special, doesn't quite help us, isn't it? Because now we at least need to relate that to one of the triangles. And all these sides here, we haven't proven that DB is equal to CD. So this is just, call it a scalene triangle. Okay? This is not an equilateral, this is not an isosceles. All these sides are just all over the place. But let's focus on the second triangle here. We have the triangle OBD or ODB. Okay. In triangle ODB, we can tell that OD and OB, those are lines that start from the center to the circumference of the circle. Okay. We have in triangle OBD. We can say that OB is equal to OD. These are ready. Right. That makes OBD to be an isosceles triangle. And if it is an isosceles triangle, like the previous question, the base angles of an isosceles triangle should be the same. So B2, this angle B2 should be the same as D1. B2 is equal to D1. Why? Base angles of isosceles triangle. Triangle what? Triangle OBD. In this reason here, you are telling us that triangle OBD is an isosceles. But where does that come from? You have already highlighted that you have identified OB and OD, that indeed those are ready. Alright? Now, if B2 is equal to D1, but we're told that B2 is equal to E, understand that we're told B2 is equal to E, we're forced to know that. And then we've just proven that D1 is equal to B2. Therefore, B1 or D1 and E should be the same. Therefore, D1 should be equal to the angle E. And then we can conclude to say, you know what, DB is indeed parallel to EA. Because now we have completed the F of DB and EA. So EA is parallel to DB. What is the reason? It's corresponding angles. Right. That is question 10.4. We can move on to the next question now, 10.5. Do we have a question on the stage?
No, just the reasoning.
Yes.
I think I'm happy with everything else. Just the reasoning. Are we not supposed to say those two are? Because I know, maybe I would remember that if you have two parallel lines and you have a transversal, which is the line that cuts both of them, your alternate angles will be equal because those two lines are parallel.
Okay.
Then now, if you find that you have two corresponding angles that are equal, now it's more like you're saying it's enough to say that those two lines are parallel.
Okay. So let's get back. Let's try to draw what you're saying here. You're saying if we had this line here, OF, which cuts in, which maybe cuts these lines that we're trying to prove are parallel.
Yeah. So
right.
if you have two parallel lines, if you have two parallel lines, right?
Yes.
And then you have a transversal that cuts them, which is the line that cuts both of them.
Yes.
Your alternate angles will be equal.
The alternate angles, okay,
will be equal, right?
Right.
No problem. Then now, in a situation where you have lines, right? And then you see two alternate angles that are equal. Is it safe to say those two lines are parallel?
So the question is that if we have a situation like this, and then there's a line here that goes like this, and we find that this angle here is the same as this angle. Therefore, those lines, it is a proof that those lines are indeed parallel.
So it's enough.
Because if these lines were like this, we can never have a Z, we can never have this angle equaling this one here. We can only have that special case if we try to push this line such that it is parallel to that. Why are we saying this? Let's maybe try and prove it. Maybe we have lines like this. Okay. We say maybe this line, we say we fix this to be parallel. Okay. We say they are indeed parallel. And if they are in parallel, then these two angles here should add up to 180, x and y should add up to 180 degrees. We're using one of the other proofs. So x plus y is equal to 180. But we already know that this angle here is in a straight line. Therefore, y plus this angle should be equal to 180. But we've just proven that in order to add any angle here to equal 180, it needs to be x. Okay, but let's say now this line is like this, and it is equal to xy. All right. we say x1 plus y is not equals to 180 because we can't link it to any of those.
Okay.
We have no way of guaranteeing that this angle here will definitely be the same as that. So if we definitely know that adding this angle and this one should give us 180. So if we can shape this line such that it is equal to this angle, therefore we can say those two are co-interior. So indeed, when you see a line that cuts two parallel lines, we can definitely say there's alternate angles. Or if you see alternate angles, then we can link that to two parallel lines.
Okay. So in that case, can you not say that now DB is parallel to EA?
Okay.
Because the corresponding angles are equal.
Corresponding
Angles equal.
By saying corresponding angles, you're already saying they are equal because the term corresponding is like saying tan chord theorem. So tan chord theorem states that the angle between the tangent and chord is equal to the opposite interior angle. All right.
Okay.
So I use that reason here. I said tan chord theorem. I should have added here and said tan chord theorem because angle between the tangent and the chord should be equal to. So when you specify the corresponding angles and you say they are equal, the information of equal is not wrong, but it is redundant.
Okay.
Because we already know that alternate angles are equal.
Okay.
You see, if you steal from my place, I'm gonna beat you. So if you already know that you are gonna be beaten, you don't have to state that stealing is wrong. Okay. Yeah, I think that sums it up. We can definitely, no one is gonna say you are wrong to say corresponding angles are equal. Okay. Right. Let's go to 10.5. Number from 5 marks. Okay, 10 point. Okay. We're going to question 10.5 now. In 10.5, we're asked to prove that DO is equal to TO times FE over AP. Okay. Okay, DO, TO, FE, and AP. The first thing you do is to identify where those sides lie. Okay, so we see DO here, we see TO in this triangle, and we see FE here, and we see AB. Where is AB? AB. All right. We can identify multiple triangles there. We can see that there's a triangle that involves OD, which is triangle ODB. We see another triangle there that involves FE. The triangle, we can try and use triangles that we have information about from previous questions. It is tough to start information from scratch now. So let's say if we look at FE, we can link it to this triangle OEF. But we haven't spoken a lot about a triangle. We have spoken about DFE, which is similar to triangle TFO, right? So we can say triangle. So here we see there's DO. In triangle DFE, we can identify that we see FE there. And then there is triangle TFO. TFO, we can identify that we're seeing TO there. Now there's this side here which is called AB. Now AB sits at a weird position there. We can not link it to any triangle there because AB forms part of this quadrilateral shape. There's ABDE, all right? ABDE. So we have ABDE. This is just a quadrilateral, a side that has a shape that has 4 sides. But something special about this shape, we can link that to what we've just proven before, that this is a special side. We can even say this is a parallelogram. But now parallelogram means all the sides, opposite sides will be parallel. But this one has one side that is parallel. So DB here is parallel to EA. Okay, we can move. So we've identified triangles we can use here. OD, DFE, TFO. Something special about these two triangles, they are similar. All right. Now, let's try to talk about this information we have, the very last information. Okay. when we have a line, if we have two triangles, we have a triangle like this, right? And you draw a line from one side of the triangle to the other side, and that line there is parallel to this line. If this angle was A, B, C, and you draw a line such that now we have D and E. Those two triangles there, or triangle ADE, is gonna be similar to triangle, say, ABC. That is the proportionality theorem. When you say something is similar, we say sides are proportional or angles are all equal. Just a quick proof there. All right.
The lines similar.
Sorry?
For a triangle.
Oh yes, yes, yes. So we have similar triangles there. What do we say here? First of all, those two triangles share point A. So we have A as one of those angles. And then if these lines are parallel, this angle is equal to this one, and this is equal to this one. So we know that those lines are proportional to each other. If lines are proportional, let's go back to this thing we have here. If lines are proportional, we can say that DE, if we say DE, let's use the black one. So DE over, so say DP here, or DE. This is the same also in this triangle, because we have DP, which is parallel to this one, and this is a triangle. This is another triangle. So we can say that those, okay, let me first make the conclusion. To say triangle ODB is similar to triangle OEA. Why? Because there's a line AB or DB parallel to line EA there in those triangles. So this is proportionality theorem. You can go for proportionality or line AB parallel to EA. Okay. So now we can, from this information, tell that if you are to take, we try to use the sides that are very important to us. So we have OD divided. So this needs to be they need to be corresponding sides. So if you look at this side divided by this side, this should be equal to this side divided by this side. Or this side divided by the whole of this side should be equal to this side divided by the whole of that side. Alright, so this is proportionality. Okay, so we can say OD is indeed OD over DE should be equal to, that ratio should be equal to OB over, what is this? BA. Right, this should also equal to, we can do for these two over the sides here, DB over EA. Alright, we can firstly identify from here that we have a side that we just identified from there. You remember I mentioned to you that AB, out of all these triangles, AB is the side that is quite, call it awkward for us, because it is not sitting in one of the triangles that or we cannot quickly link it to one of the triangles we're working with. But now we've just linked it via this formula here. Or we can use this one. But what is special about OD and OB? OD and OB, that's a radius. Like this OD is a radius and OB is a radius. We can make a conclusion here that if this is equal to this one should definitely be equal to this one, because this ratio must be maintained. So we can conclude from here that since, okay, since OD is equal to OB, I don't have to state this, we've been talking about it previously. Therefore, DE should indeed be equal to angle AB or BA. I'm writing it as AB so you can at least identify it as one of those sides there. Okay, so now we can link DE or AB to one of the sides. Okay, now we can go back to these ones that we have here. Alright. If we go back there, we have similar triangles there. Because now we have AB and we have DE. DE doesn't exist there. But okay, we now have to link TO, FE, and maybe DO. Alright. So we can say that here, if these are the same, if these are similar, if we divide corresponding sides, those ratios should be maintained. Corresponding sides, how to use corresponding sides? You look at the angles around those sides. So if you see that this side here, OF, there it is, it has the angle O2 and F2. And this angle is equal to this one is equal to this. Those are corresponding sides. You can't say this side divided by this one because those sides are not linked by the same angles, all right? So we can say the side OF over the side FE, corresponding sides. These are the angles that are corresponding. We can say that is equal to, we use maybe this side here. See, there's that angle, 3 lines and 1 line. 3 lines and 1 line. So there's TO and DE. We can go for the other side, which is the remaining one is just TF over DF. But these sides here don't say anything on this equation we're trying to prove. So we can focus on this side because OF, or let's see, FE is there, TO is there, and DE, okay, DE is not there, but we have linked DE to AB. First thing we can say from here is that because of this remark here, we can say that OF over FE, this should be equal to TO over AB. Are you with me? DE is the same as AB, we've just proven that. So we can say that this ratio should also be the same as this one, all right? But now, what is OF? Because they were asked to make DO to be the subject of the formula. But what is special about DO or OD? OD is just a mere radius because it's a line from center to the circumference. But what is OF? OF is also a radius. OF starts from the center to the circumference. We can tell that, we can say here, since OF is equal to DO, these are radii. We can then say here, this is DO over FE equals to TO over AB. And to make DO the subject of the formula here, just multiply by FE both sides. Therefore, DO is equal to TO FE over AB. We have proven that expression there. Alright guys, that marks the end of this question. Please, if you have questions, leave them in the comment section below. Don't forget to like, subscribe, and refer to the video to many more people. Thank you.